Hello everyone, welcome to this video lecture of 19ScPhyU301. We will begin the discussion of the third chapter, vector analysis, from this lecture. Our plan in this lecture is to revisit the basics of vectors. We will discuss dot product or scalar product, then cross product or vector product of two vectors. We will also discuss triple products. This is the scalar triple product and vector triple product of the vectors. Let's begin from discussion of scalar product of two vectors. Suppose I have these two vectors. This is vector A and this is vector B, and suppose the angle between them is theta. Then scalar product of these two vectors is denoted like this: A dot B, and by definition it is equal to mod A mod B into cos theta. This A mod A is the magnitude of vector A, B is magnitude of vector B, and theta here is the angle between the two vectors. Now by definition this product of two vectors is a scalar quantity, and therefore it is called as the scalar product of two vectors. So this is how scalar product is defined. Now it should be very clear that here we are multiplying these three quantities: magnitude of A, magnitude of B and cos theta, and therefore we can always rearrange this to write A dot B as magnitude of B, magnitude of A into cos theta, and therefore we have A dot B is equal to B dot A. One important application of dot product comes when we want to find out the projections of the two vectors. Suppose this is vector A and this is vector B. This angle is theta. Let me resolve this vector A into two components, one which is parallel to B. For that I have to drop a perpendicular from head of vector A to vector B. So therefore if this is the perpendicular, then this is component which is parallel to B. I am denoting it like this, whereas this component is perpendicular to vector B. Let me denote that by A perpendicular to B. Both are vector quantities, and then magnitude of the component which is parallel to vector B is called as projection of vector A onto vector B. Now note that this projection is always a scalar quantity. We are considering magnitude or length of the component of A which is parallel to B. Now to find the projection, note that this is a right angle, and therefore I can write cos theta as adjacent side of the triangle, which is this length, projection of A onto B, divided by this hypotenuse, which is magnitude of vector A, which is length of vector A, and therefore this length, which is projection of A onto B, is equal to mod A into cos theta. With this formula now we can easily find projection of a vector onto other. It can be worked like this. Let me first find A dot B, which is equal to mod A into mod B into cos theta, and therefore this projection of A onto B, which is mod A cos theta, is equal to A dot B divided by mod B. So this way we can get projection of A, vector A onto vector B. Now it is very straightforward. to find projection of vector B onto A, what we have to do is we have to consider this resolution of vector B, this component which is perpendicular to A and this component which is parallel to A, with this angle as 90 degrees, and rest of the things will then be same, and we will get projection of B onto A as mod B cos theta, which is equal to A dot B divided by magnitude of A. This is a vector. So this quantity then gives us projection of vector B onto vector A. Suppose we are given vector A and vector B as their components AXI plus AYJ plus AZK, where AX is X component of vector A, AY is Y component of vector A, and AZ is the Z component, whereas these I cap, J cap and Z cap, sorry, K cap are the unit vectors along X axis, Y axis and Z axis respectively. And suppose B is equal to BXI plus BYJ plus BZK, and we want to find this dot product A dot B in terms of the components of the two vectors AX, AY, AZ, BX, BY, BZ. Then it can be done in this way. Vector A is now AXI plus AYJ plus AZK, and we are taking dot product of this with BXI plus BYJ plus BZK. Now when we expand these two brackets, what will happen is we will get 9 terms. The first of them I'll write AX into BX into I dot I. So in this way we will have 9 terms, where this bracket in each of these term is going to be product of two scalar quantities, and the second bracket is the dot product between the unit vectors. Now by definition, dot product between two vectors V and W is mod V into mod W into cos theta. Therefore, when we find dot product between two same unit vectors is 1 into 1, and since the vector is same, angle between the two vectors is 0 and cos 0 is equal to 1. So this I dot I turns out to be equal to 1. Similarly, J dot J is equal to 1 and K dot K is also 1, and this is all these three is equal to 1. Whereas if we consider dot product between two dissimilar unit vectors I dot j, then this is magnitude of I is 1 into magnitude of j is 1, but since theta now is 90 degrees, cos theta will turn out to be equal to 0, and therefore dot product between two dissimilar unit vectors is going to be equal to 0. By keeping this in mind, suppose we expand these brackets. Now what will happen is, out of the 9 terms that we get, 6 terms will be 0 because they will be dot product between two dissimilar vectors, and what we will get in the end is this. It will be AX BX plus AY into BY plus AZ into BZ. So A dot P therefore is this quantity. Suppose we want to find dot product between two vectors in terms of their components along x, y and z axis, then we can use this formula to find the dot product. Now let's consider one application of dot product. We are given a force, this is a vector, then this is, these three are the unit vectors. So we are given this force and this is acting on an object which undergoes displacement of this due to that force, and we want to find the work done by the force. It's simple. F vector, let me write it down. It is 2I minus 3j plus k, this is j, and displacement r is I minus 5k. These are also unit vectors. They are denoted by this cap symbol. Work done, therefore, which is a scalar quantity by definition, and it can be calculated by taking dot product between the force and displacement, or work done is 2I minus 3j plus k dot product with I minus 5k. So therefore this is equal to 2. We have j component or y component as 0 for the displacement, and therefore only x component and z component of force will do the work. So what we get is 2 into 1, and finally we have to multiply the z component of force and the displacement, which is plus 1 into minus 5. So let me write down minus 5 for that right away, which is equal to minus 3. Now since we don't know the units of the force and the displacement, I'll simply write unit here, because it is clear that since this is work done, it should have dimensions of energy. Now depending on what are the dimensions or what are the units of force and displacement, we have to decide on what unit that work done has. Let's quickly discuss the other kind of multiplication between the two vectors, which is called as the cross product. And since the multiplication gives a vector, it is called as vector product of two vectors. This is vector A and this is vector B now, and the angle between these two vectors is theta. Cross product of these two vectors A cross B is denoted like this, and by definition this quantity is a vector. In fact, that is the reason why it is also called as vector product of two vectors, in comparison with scalar product or dot product, which gives us a scalar quantity as output. So this cross product has magnitude which is equal to mod A cross B is mod A mod B into sine theta now. So this is how magnitude of cross product of two vector is calculated, whereas the direction is given by using right hand thumb rule. To find the direction of cross product of two vectors, you have to hold your right hand in such a way that the four fingers are curled, and these curled fingers denote the direction of rotation from vector A to vector B by an angle which is less than 180 degrees. So here in this case we have to rotate in this direction, and that's why the fingers are denoting the rotation from vector A to vector B along an angle which is less than 180 degrees, and then the thumb gives the direction of the cross product, which is perpendicular to the plane which contains vector A and vector B. So in this case, this red arrow, this red vector denotes the cross product of two vectors. So it is basically A cross B vector, and therefore direction is given by right hand thumb rule. So this vector product of two vectors now has magnitude given by this relation, and its direction is to be calculated by using right hand thumb rule. When we defined the dot product of two vectors, we saw that A dot B is equal to B dot A. Now let's see whether the vector product commutes or not. Suppose this is vector A and this is vector B. Now A cross B has magnitude which is equal to mod A into mod B into sine theta, and the direction now is given by the right hand thumb rule. We have to hold the right hand such that these curled fingers denote the rotation from A to B along an angle which is less than 180 degree, and therefore A cross B is in this direction, upward direction in this case. Cross product B cross A, and the magnitude is going to be same. It will be mod A into mod B into sine theta. But what is the direction? Direction of this cross product is to be calculated by considering the right hand rule, right hand thumb rule. We have to rotate from B to A and then hold the fingers of right hand in such a way that they denote the rotation from B to A, and then thumb denotes the direction of the cross product B cross A, and therefore you can now compare that the direction of A cross B and B cross A are opposite, and therefore what we have is A cross B, which is equal to minus of B cross A. Note that they are going to have the same magnitude, which is mod A mod B sine theta, but the direction is opposite, and that's why we have the relation for cross product of two vectors like this. Let's now see how we can write the cross product in terms of components of the two vectors. For that, let me first consider this coordinate system. This is x-axis, and therefore this is the direction of unit vector I. This is unit vector of j, and this is unit vector k. So this is x-axis, this is y-axis, and this is z-axis. Always keep in mind that we use right hand coordinate system, which means that if I hold the right hand in such a way that the curled finger denotes the rotation from x-axis, positive x-axis to positive y-axis, then thumb always gives the direction of z-axis, which is unit vector k. It is never the other way around, so therefore it will be wrong for me to assume that this is y-axis and this is x-axis. It is wrong because if we rotate from x-axis to y-axis, we get the z-axis in this direction, and if we consider that these are x and y-axis, then z-axis will be in downward direction. Now here I want to find the cross product I cross j. Now since I and j both are unit vectors, magnitude is equal to 1, and therefore this is going to be mod I, which is 1, into mod j, which is 1. The angle between these two vectors is 90 degrees since these are the unit vectors, and the direction is given by right hand thumb rule, which is along direction k. So I cross j is equal to k. If I consider this cross product now, j cross k, then you can see that it is equal to I, and for this diagram, this is unit vector I, this is unit vector j, and this is unit vector k. This also is k. So if we consider this cross product, which is k cross I, it is always equal to j. On the other hand, if we consider cross product j cross I, it will be equal to minus k. K cross j will be minus I, and I cross k is minus j. On the other hand, if we consider cross product between the two same vectors, it will always be equal to 0. That is because I cross I is 1 into sine 0, because they are the same vectors, angle between them is 0, and therefore it will give us 0. And this is true for j cross j as well as for k cross k. Now suppose we are given the two vectors A, which is axi plus ayj, plus azk, and vector b, when it is written in component form, is bxi plus byj plus bzk, and we want to find out the cross product. A cross b is equal to axi plus ayj plus azk, cross product with bxi plus byj plus bzk. Now when we expand these two brackets, we will again have 9 terms. 3 of the terms will be cross product between the same vectors. Ax, bx, I cross I will be 0. Similarly, for this term, j cross j will be 0, and for the last term, k cross k will be 0, and we will have only 6 terms which are non-zero out of the 9 terms that we have after expanding the bracket. Let's find them. So what we will have is ax by I cross j plus ax bz I cross k plus ay bx j cross I plus ay bz j cross k plus az bx I cross j, sorry, k cross I plus az by j cross k. We can use these relations for cross product between two unit vectors, and these terms, the first brackets in all the 6 terms, are the scalar quantities. After doing this mathematical jugglery, what we will find is this a cross b can be written as this matrix I j k ax ay az bx by bz, and this cross product will be I ay bz minus az by minus j ax bz minus az bx plus unit vector k ax by minus ay bx. So in this way, by calculating this determinant, you can find the cross product between the two vectors, and cross product of the two vectors now is governed by the laws, by the rules of calculating matrix, and therefore it is easy to show that a cross b should be equal to minus b cross a. Why? Because for this determinant we have to interchange this rows once, and when we interchange rows once for a determinant, the value of that determinant is reversed in sign. So this is how you can find the cross product of two vectors. Let's consider one application. So what we have is this force. This is the force which is acting at this point. So let me consider that this is the point with x coordinate as 3, y coordinate as 2, and z coordinate as 1, and therefore position vector for this point where the force is acting is 3i plus 2j plus k. And just as a representation, let me consider that this is the force, and we want to find the torque due to this force at the point. So this is vector torque is given by this cross product R cross F, where R is the moment arm. Therefore this is equal to R is 3I plus 2J plus K, and we are taking cross product of that with 2I minus 3J plus K. This cross product is going to be determined by this determinant I, J, K, 3, 2, 1, and this is 2 minus 3, 1. This is now 2 plus 3 minus J into this multiplication 3 minus this multiplication, which is 2, plus K into this multiplication, which is minus 9, minus this multiplication, which is 4. Therefore this is equal to 5I minus J minus 13K. So the torque is now a vector quantity, and it is given by this vector. Although we are not getting into details of these quantities like torque, which are calculated by taking cross product of two vectors, are called as pseudo vectors. In comparison with these vectors such as displacement and force, which are called as the axial vectors. One reason that they are called as pseudo vectors is because they do not satisfy the commutation relation for addition of the vectors, which is basic requirement for a quantity to be defined as a vectors in mathematics. Let's consider one geometrical application of two vectors. This is vector A and this is vector B, and suppose I find out A cross B. Let me stick to the magnitude of that, which is equal to mod A into mod B into cos theta. To see what is happening here, let me complete this parallelogram, where I am drawing this vector A at the head of vector B, and I am also drawing vector B at the head of vector A. Okay, this doesn't look like a parallelogram. Now let me drop a perpendicular from here, head of A, onto B. So this perpendicular, let's say h is height of that perpendicular, and if the angle between the two vectors is theta, this is to be sine theta, sorry, then from this triangle, from this right angle triangle, we can see that h is equal to b sine theta, and therefore this magnitude of A cross B is actually magnitude of A into h. Now magnitude of A is this length, which is base of the parallelogram, and h is height of that parallelogram, and therefore A cross B, or magnitude of A cross B, gives us area of parallelogram formed by the two vectors. Let's now consider scalar triple product. Let me suppose this is vector B, this is vector C, and this is vector A. So these three green arrows are the vectors for which we are calculating this scalar triple product, which is defined like this. It is A dot B cross C. This term B cross C is a vector quantity. Let me call that as D for a while. And therefore, what we have for scalar triple product is A dot D, which in the end is the dot product between two vectors, and therefore this right hand side will be a scalar quantity, and therefore the name scalar triple product. Before we write the scalar triple product in component form, first let's see a geometrical interpretation of that. Suppose I first consider this cross product B cross C, which is vector D. Then we just saw that when we consider the cross product of two vectors, it gives us area of parallelogram, which is formed by vector B and C in this case. So for vector D, its magnitude is same as area of this parallelogram, which is forming the base of the parallelepiped, which is formed due to the three vectors A, B, C. These three vectors A, B, C are now the edges of this parallelogram. What is direction of vector D now? Its direction is to be calculated by using right hand thumb rule. So we have to hold our right hand in such a way that the four fingers are curled along the direction of B to C, and then thumb gives the direction of the cross product B cross C, and therefore in this case direction of vector D is given by this upward arrow. Now what we are doing is we are taking dot product of A with this D, which is going to be equal to mod A mod D into cos theta, where theta is the angle between vector D and vector A. So theta is this angle. Therefore, this now is going to be equal to mod A into cos theta into magnitude of vector D. Now what is this term? A mod A cos theta. It is basically this dashed line, because this angle is theta and this vector is A. So if I complete this triangle, this angle now is 90 degrees. Then A cos theta is this length, which let me call as H. Therefore, A cos theta is height of the parallelepiped. So this is height of parallelepiped, which is formed by the three edges of the vectors for which we are taking the dot product, and into magnitude of vector D is area of that parallelogram. Therefore, this scalar triple product A dot B cross C gives us volume of the parallelepiped. In the beginning, I said that these three vectors A, B and C, we are taking this scalar triple product, they should not be in the same plane, they should not be coplanar, and the reason should be now clear. It is because if they were lying in the same plane, then the parallelepiped would not be formed. The volume of that will be 0, and therefore the scalar triple product will also be 0. Let's see how scalar triple product can be calculated when we know the components of the three vectors. So this A dot B cross C is equal to A dot, and B cross C is calculated by this determinant ijk bx by bz, and Cx, Cy, Cz. Now it is straightforward to see that this actually is going to be the determinant Ax, Ay, Az, Bx, By, Bz, and Cx, Cy, Cz. Let's consider two interesting things about this scalar triple product, and they stem from the way you calculate them. This is the determinant that gives the value of the scalar triple product, and therefore as a consequence of properties of this determinant, it is easy to prove that if we are calculating this scalar triple product A dot B cross C, it's same as B dot C cross A, and that is equal to C dot A cross B. So for a scalar triple product, if we change the order of the vector in cyclic manner, if we change the order cyclically, then the value of the scalar triple product is unchanged. Whereas if we break that cycle, if I consider this scalar product now, scalar triple product now, B dot A cross C, then that is going to be equal to minus of B dot C cross A. The reason should be clear here. A cross C is equal to minus of C cross A. Similarly, if we interchange the dot and cross symbols, so in this case, if we interchange this dot, if we bring it here, and if we take this cross product here, then what we get is A cross B dot C, and they are always equal. You can see that that is basically this third term, C dot A cross B. So these are some relations governing the scalar product, scalar triple product. Let's now consider vector triple product. Suppose this is vector A, this is vector B, and this is vector C. Then vector triple product is defined like this. It is A cross B cross C. In this diagram, this dashed line here, so this parallelogram basically is the plane in which vector B and C are present. Now when we calculate this cross product B cross C, let me write that as D, then this cross product is going to be perpendicular to the plane which contains B and C, and therefore this is going to be the direction of D, which is the cross product of B and C. Now what we are doing is we are taking cross product of A with the resultant vector T, which is basically A cross B cross C. So we now are taking cross product between this vector A and the vector D. Its magnitude is of course going to depend on what is magnitude of A, B and C, but this A cross D now has the direction which is in the same plane as the plane of the parallelogram. Therefore, this A cross D now is going to lie in the same plane as that of B and C. You can check that by using right hand thumb rule. If you hold your hand such that there is rotation from vector A to vector D, which is denoted by the four curled fingers, then thumb denotes the direction of the resultant vector. It should be clear that when we calculate this A cross B cross C, this is a vector quantity because this is a vector and we are taking cross product of two vectors. So this vector, which is resultant of vector triple product, lies in plane with vector B and C. So the scalar triple product is always going to lie in the plane which contains vector B and vector C. Let's use this fact to find the relation for vector triple product. Suppose we are finding this vector triple product A cross B cross C. Now you should realize that this vector triple product is lying in the plane which contains B and C, and therefore we should be able to write this as a linear combination of two vectors B and C. This is possible because we know that this triple product, vector triple product, lies in the plane which contains B and C. Also note that it is obtained by taking cross product of A with B cross C. This B cross C is another vector, and this triple product should always be perpendicular to vector A because it is obtained by cross product of A. So this triple product is always perpendicular to vector A. Now given this fact, what will be the dot product of vector triple product with A? It should be now equal to 0 since these two vectors are perpendicular to each other. Therefore, what we have is A dot B into B plus C into C should be equal to 0. So here for this step, I have used the right hand side of the first relation that we have written, and what we know now is B into A dot B is equal to minus C into A dot C. Let me rearrange this equation to write B divided by A dot C is equal to minus C divided by A dot B. Now both these terms are scalar quantities. Let's say that this is equal to some scalar which I am denoting as P, and therefore what we have now is this A cross B cross C is equal to B, the scalar B here is equal to P into A dot C into B, and C, which is scalar here, is minus of P into A dot B into C. This is equal to, I can take P common, and this is A dot C into B minus A dot B into C. Note here that this is a dot product and therefore is a scalar quantity which is multiplied by vector B, so this should be a vector. Similarly, A dot B is a scalar which is multiplied by C, and therefore that should also be a vector, and therefore on right hand side we have a vector quantity which is expected because left hand side is a vector quantity. Now the whole problem of finding vector triple product has boiled down to finding this scalar P. To find the scalar P, we will take shortcut. We will consider a special case where A is equal to I, B is also vector I, and C is equal to vector J, and we will consider the cross product, vector triple product between these three vectors. This suppose is x-axis, this is y-axis, and this is z-axis. Therefore A cross B cross C in this case is I cross J, which is equal to I cross K, which is equal to minus J. So for this special case, it is easy to find the vector triple product. Now we will use this right hand side here, which gives us A cross B cross C is equal to P is unknown. We have to figure out what is P. A dot C is I dot J, which is equal to 0. So the first term will vanish. Second term is A dot B, which is I dot I, which is equal to 1, and C is equal to J. And therefore what we have as A cross B cross C, if we use this relation here, is minus P into minus J. Now if we compare these two triple product, it is easy to see that P is equal to minus 1, and now we can write the relation for the vector triple product in terms of A, B and C. P is equal to, sorry, it is not minus 1, it is equal to 1, and therefore the triple product is equal to A dot C into B. So you take dot product between first and third vector, which is a scalar quantity, and that is multiplied by vector B, minus the second term is now the dot product between the first and second vectors. So it is A dot B, which is multiplied by vector C. So this is how you can find the relation for A cross B cross C. Although we have considered a special case for obtaining this relation, the relation turns out to be correct. We have come to the end of this video. Let's quickly summarize. We have seen the two ways to multiply two vectors. In this first way, it is called as the dot product, and by definition this dot product gives a scalar as the output, and therefore it is called as scalar product of two vectors. Whereas in this second case, which is denoted as A cross B, the output is a vector quantity, and therefore it is called as a vector product of two vectors. A dot P is equal to mod A mod B cos theta, where theta is the angle between the two vectors, and magnitude of A cross B is mod A mod B into sine theta. Its direction is given by the right hand thumb rule. We have to hold the right hand in such a way that four fingers are curled in the direction from A to B, where the angle is less than 180 degrees, and then thumb gives the direction of the cross product. We also saw two ways to multiply three vectors. The first is this A dot B cross C. Now you can see that this B cross C is a vector quantity, and we are taking dot product of these two vectors in the end, and therefore this is a scalar quantity which can be calculated with this determinant AX, AY, AZ, BX, BY, BZ, CX, CY, CZ. This is a vector product. It is A cross B cross C. Now B cross C is a vector, and then in the end we are taking cross product of two vectors, and therefore this turns out to be a vector quantity which can be calculated by this equation. We take dot product of first and third vector, so it is A dot C, and it is multiplied by the second vector B, minus the next term is dot product of first and second vectors A dot B, and it is multiplied by the third vector C. So this is the relation which can be used to find the vector triple product. In next lecture we will consider the concepts of scalar and vector fields, and we will see how we can differentiate a vector with respect to a scalar. That's all for this video. Thank you for watching.